Good morning students, welcome to the next class of Programmable Logic Arrays of STLD subject. In this class we will discuss the Programmable Logic Arrays. So see here, in the previous class we have discussed about programmable read-only memory where the PROM is the memory device, and after we discussed the programmable array logic where the programmable array logic which has the freedom of connecting the AND gates based on the user's choice, that is programmable AND gates are available, and industry specified or gates, that is fixed OR gate arrays are available in the programmable array logic. In the programmable read-only memory we have the freedom of connecting the OR gate inputs based on our requirement, but AND gates are the fixed AND gate inputs connections we have taken in the form of decoder. So that is about PROM and PAL. Now coming to that programmable logic array, now we are implementing programmable logic array. So where programmable logic array has the inputs to the programmable AND array, and here we have programmable array OR array. So both AND gates and OR gates both are here programmable. Okay, right. So both gates are programmable. For this, both gates are here. If you want how many number of inputs you require for the AND gates, how many number of OR gates you require, that is based on your requirement you can connect. That is, here we have the free hand to the all the gates. So see here we have AND gates, here we have the OR gates. For the AND gates, here we have the flexibility to connect. That is, I have given the programmable connections with the into mark representation. Here for the OR gate also I have represented, that is with the into mark representation. That may be that is nothing but as you can take here 2 input AND gate or 3 input AND gate or 4 input AND gate. Any type of AND gate you can take here and you can give the inputs. Otherwise you don't, if you don't require, you can remove that gate also. That is, there is no rest of taking that AND gate. Here for the OR gate also you can use here 2 input OR gate. Otherwise you can take 3 input, you can take 4 input, whatever it may be. So both gates are depends upon your choice only. There is no vendor choice here. In the previous topics of PROM and PAL, we have the we don't have the flexibility or programmability for one type of gate arrays. Here for these two types of gate arrays we have the flexibility. Whichever the gate you require you can use, whichever the gate you don't require you can leave that gate. Right. Next we will see one example. Here the problem is implement the following Boolean functions using PLA. So here they given two functions. F1 is equal to AB bar plus AC plus A bar BC, and F2 is equal to AC plus BC whole bar. Okay, these two are the simplified expressions. Here these two are the simplified expressions. So see here, is there any chance to simplify this expression? Is there? So if you take the common C, A plus B into C whole bar. So if you take the common also, there is no possibility to reduce the gates. Okay, so this is the simplified version for F2. And next coming to for F1, AB bar plus AC plus ABC bar. So is there any chance to reduce that expression? Here there is any chance B to take B common? No. A common, no. If you take the common, there is no possibility. Right. So there is no chance to take there is no possibility to minimize that F1 expression also. See that two F1, F2 expressions. First, what is the condition here? Check that is there any possibility to minimize the expression. So the first condition, check the reducing is possibility or not. Check the reducing is possibility or not. So for the given function, is there any possibility to reduce that function? So there is no possibility. Here we don't have any possibility to reduce the expression. Okay. Now identify how many number of AND gates you required. Here 1, 2, 3, 4, 5. Totally 5 AND gates are required. Here AC is repeated here. AC is repeated here. So for that reason, totally you required only 4 AND gates. Total you required 4 AND gates. You required only 4 AND gates. Okay. So with the 4 gates, with the 4 AND gates, you can implement this function. And for F2 function, you required 2 input OR gate 1, and for F1 function, you required 3 input OR gate. Okay. So first you have to draw the A, B, C, and A bar, B bar, C bar signals. Actually, here I have B bar, A bar, C bar, and A, B, C. Total 6 different types of literals are available. So here I have drawn A, B, C, A bar, B bar, C bar. Totally 6 input lines I have drawn here. Actually 3 input lines only, but why I said that 6 input lines, remaining 3 are A bar, B bar, C bar. Okay. Next, I have drawn the 4 AND gates. So second step, we have to identify the how many AND gates required. Second step, you have to identify the how many AND gates required. Right? So I said that 4 AND gates are required. These are the 4 AND gates I have placed. And how many OR gates required? So I required 2 OR gates. So for that I have drawn 2 OR gate lines and I have represented with 2 OR gates. Now I am making the connections. So see here. So here I have A bar, A, B bar. So see here, this is A and this is a B bar. So the first AND gate output is A, B bar, and next one AC. So A and this is C. So this AND gate output is AC. Next A bar, B, C bar, A bar, B, C bar. So this is next one, A bar, B and C bar. So this is A bar, B, C bar. So this is the third AND gate. So this is also over. AC already we have represented, and B, C. So this is B and this is C and this is C. So BC. So the last gate is BC. So these are the AND gates we have taken based on our choice. Okay, so sometimes I have taken 2 input AND gates and sometimes I have taken 3 input AND gate. Okay, so all the gates I have taken here. Now coming to that, the first function F1. So this is the F1. F1 is equal to A B bar plus AC plus A bar BC, A bar BC bar. So that is the first function. So here I have taken the function directly. So that is the 3 input outputs I have taken here. I have mentioned there, right? From that I have taken 1 OR gate. So I got finally F1 function. Next here F2 function AC plus BC whole bar. So AC I have taken and BC I have taken. So here this is AC, this is BC, this is AC and this is BC. These 2 inputs are connected to an OR gate. So I got AC plus BC, but I have to implement AC plus BC whole bar. Right? Programmable logic array, it has only 2 stages. One stage is AND gate, another stage is OR gate. First stage is AND gate, second stage is OR gate. But AC plus BC I got here, but I want AC plus BC whole bar. I want AC plus BC whole bar. Then how I have to implement this function. Then how I have to implement this function. So for that reason I am taking 2 more now. So here for this function, just you have to take the inversion operation. But in some of the devices, we don't have the flexibility of taking the NOT gate. So for that reason, I am taking the exclusive OR gates. So see here, for the 2 outputs, I have taken 2 XOR gates. 2 XOR gates. So F1 I have connected to 1 XOR gate, and F2 I have connected to another XOR gate. Right? Here we have a small function. See here. You have an XOR gate here. Here I am giving the function F1. Okay, right. Now here I have 1 more input and here we have output. Actually I said that AC plus BC whole bar I required. Here I got AC plus BC. I got AC plus BC. That is, for example, F1 may be available. Otherwise you can think that here some X is available. Okay, so in the place of X I have AC plus BC, but I required AC plus BC whole bar. That is, I required here X bar. Okay, so but in between X and X bar I have XOR gate operation. So go with XOR truth table. Go with XOR truth table. So this is the XOR truth table. So here X is there. This is the unknown value. It may be 0 or it may be 1. It may be 0 or it may be 1. So this may be 0, this may be 1, the X value, I don't know. If I have kept here 0, that is one of the XOR gate input terminal I have kept it to 0. So if now I have kept the 0. So see here, for example, I have kept the 0 here. So for that reason I have removed these two conditions. Why? Because if I kept one input is 0, automatically, so the second input may be 0 or 1. So these two combination will only occur. So for this, see here, here the one input is 0, second input is B. If B is equal to 0, output is 0. If B is equal to 1, output is equal to 1. That is, here with using only one input you can decide what is the output. For the XOR gate, if one of the input is equal to 0, then output is equal to the other input. Okay, here I have, for example, X and Y, where Y is equal to 0. That is, one of the input of XOR gate is equal to 0. That is fixed. If that is fixed, then the output is equal to input. That is, the output is also X. But what I required finally here, X bar I required. So for that reason, Y is equal to 0 I have verified. Now I will take Y is equal to 1. Y is equal to 1. Now I will take. Right. Now we will see the next combination. Now Y is equal to 1. So that is one of the input is equal to 1. So for that reason I have removed these two conditions. So now see here, if B is equal to 0, output is equal to 1. If B is equal to 1, output is equal to 0. Here the XOR gate is we can define like this. If one of the input for the XOR gate is equal to 1, then output is equal to the other input complemented form. That is, if here it is X, then it is X bar. When Y is equal to 1, that is one of the input is equal to 1, then automatically the output is complemented of the second input. So see here, actually here AC plus BC operation we are getting. So the XOR gate output should be AC plus BC whole bar. So for that reason, so the one input is F2, that is AC plus BC. This is AC plus BC. Another input I am fixing for 1. Another input I am fixing for 1, and if it is 1, the XOR gate, what it does, the output of the XOR gate is the complement of the another input, the complement of the another input. For example, if here we have X, then we will get X bar. In the place of X, if you have AC plus BC, then output is AC plus BC whole bar. Here, if you kept X is equal to AC plus BC, then X bar is equal to AC plus BC whole bar. So finally, what we required here, AC plus BC whole bar. Now here X bar is equal to AC plus BC whole bar. AC plus BC whole bar. So this is the way how to implement the operation. Now coming to the second. So here, if you are using any modification for the one terminal, the same modification you have to done for the all the outputs. So here I have placed XOR gate. Here also you have to place XOR gate. Here actually we got the function. What are the function here? We got the function is our required function in the given problem. There is no necessity of doing the modification. So for that reason, for this second XOR I am giving the input is 0. Second input is 0. So this is the finalized functions. These are the finalized functions. So see here F1 and F2 functions I have represented here, and here I have given one input is 1 and another input is 0. Here the input is 1, here the input is 0. Right? So here this is a function F2, this is a function F1. Okay, right. So this is the way of implementing the given Boolean function by using programmable logic arrays. Programmable logical arrays. Note it down. Okay, right. Now coming to the programming table. So this is a programming table for programmable logic arrays. Majorly we are writing programming table for the programmable logic array type of devices. Right? So see here, programmable programming table, where the programming table we are defining it is nothing but as it is seems to be whatever the connections we have framed based on the connections, this type of tables we are writing. So see here, how many product terms are available in the previous problem. So see here, F1, F2, here we have, now from the F1 AB bar and plus AC plus ABC bar, that you have to write down here. First AB bar, next AC, next BC, next A bar, B bar, C bar. So these are the product terms. This is the first part of the programming table. So next coming to the second column. Next coming to the second column. In the second column, you have to write down the all possible inputs A, B, C. Here I have A, B, C, 3 inputs. So this minterm is covering which input value. So A is there. So A, it is matched. Okay, no problem. We have to represent one. And here it is B bar. B term it is covering with the complement operation. That is in the form of 0 it is covering. And here in this product term C is not available. Represent with dash. Represent with dash symbol, and here AC is there, A value 1, C value 1 and B is not available. Here BC is there, B value 1, C value 1 and C, A is not available, and A bar, B, C bar. And A bar, B, C bar. A bar is equal to 0, C bar is equal to 0 and B value 1. Like that we have to make the programming table. The same programming table we have mentioned here. Next coming to that, finalized outputs. Here we have written inputs and here we have to write the outputs. That is F1, F2. Right. So the first product term A, B bar is covered or not for the F1 function. That you have to check. Okay. So for the F1 function, so check the previous table from the previous table. So see here, the F1 function covers AB bar, AC plus A, B, C bar. That is AB bar it covered and AC it covers. BC is covered by the second function F2. Second function F2 and AB is A bar, BC bar is covered by the first function and AC is also covered by the second function. So here AB bar is not covered by F2 function, BC is not covered by the first function and A bar, BC bar is not covered by the second function. So here this table, this programming table gives the information how many inputs we have utilized and how many outputs we have utilized and which function is related to which minterm. This type of details they will provide. So based on this, they will identify how many number of gates we required, how many number of input lines we have to keep, and what are their configurations. This is nothing but as when you are implementing an hardware for the given Boolean function, this programming table will give the minterm specifications and input specifications. So see here, the A is required in the form of A bar and A, and B is required in the form of B, B bar, and C is required in the form of B, C, C bar. So with the help of zeros and ones you can say clearly. And F1 is implementing with 3 minterms and F2 is implementing with 2 minterms. For the small function there is no necessity of this programming table, but when you are implementing the biggest function, this programming table gives a lot of help for implementing the hardware. So for that reason programming table is very important. Okay, so don't forget this programming table. It is very important and it is essential for implementing the programmable logic array devices. Okay, PLA devices. With this we have completed programmable logic array type devices. Totally here we have implemented, we have seen the concepts of programmable logic devices. In this programmable logic devices, now I am giving the summary. So we have seen the introduction to PLDs, okay, programmable logic devices we have seen. So in this, first we have discussed the basic structures of 3 types of PLDs. So in this we have seen three types of basic structures for PLA, PAL, PROM, and after that we have seen the implementation part by taking some Boolean functions, how to implement by using those type of structure technology, that is implementation. So we have implemented different types of Boolean functions by using these three types of PLDs. After that we have seen programming tables. Next we have seen the programming tables for these three types of functions. For these three types of functions we have, for PLA type of functionality we have seen, and actually programming table is not that much of required for the PROM structure and PAL structure, but anyhow we can write. Why? Because in the PLA side, for the inputs, for the outputs, for the both sides we have given the that is the specifications of the functionality, but in the PLA or PAL side we can give any one side only the flexibility. Why? Because the other side we are fixing the values, right? So this is about the structures. Now finally come to that the comparison between PLA and PAL. So coming to that PLA, programmable logic array. Programmable logic array side, AND gates are programmable, OR gates are fixed. Sorry, programmable AND gates and OR gates. There is no list of fixing. And the PAL side, fixed OR gates we are using and programmable OR gates we are using. Next coming to that availability. So this is less prophylactic. That is PLA is very costly devices. Generally this type of devices are not preferable in the smallest applications, and PALs are generally readily available at the some of the locations. And flexibility, so PLA has more flexibility and PAL has less flexibility. And cost, so if the choice is there for the changing the program for the devices, then that is very complex to design. So that PLAs are very costly and PALs are very cheap with compared to this one. And number of functions, we can use any number of functions and any number of times, but here it has, with compared to that PLA, it has some limited functionality. And coming to the speed of the device, so this is somewhat slow and it is somewhat high. Why? Because these are the predefined functions and some limited functions are available, so it is very speed, but it is compared to that PLA, it is somewhat slow. Okay, like that you have to read the differences between PROM, PLA, PAL. These three types of devices and comparisons are required to get the good knowledge about this programmable logical device. So for that reason, don't forget about these all other things. It's very important and essential. Okay, thank you.